Did the Jack Dungara won the Turing Award from the ACM announced today.
Great.
Wow.
Did the Jack Dungara won the Turing Award from the ACM announced today.
Great.
Okay, so we're a minute or so past the hour, so we can get started for today's ENLA seminar. So I'm Alex Townsend, I'm at Cornell University, and I'm the chair for today. So our speaker is Alison Ramage from the Department of Maths and Statistics at the University of Strathclyde in Glasgow. And Alison is well known to us on the call as an expert in numerical linear algebra. She focuses on efficient solution methods for partial differential equations and preconditioning linear solvers, as well as the topic of today, data assimilation. She is the co-developer of the IFIS toolbox for modeling incompressible flows, which is written in MATLAB and Octave. IFIS is just a really useful package if you want to implement mixed finite element approximations of incompressible flows, and maybe a playground for experimenting with preconditioners. So if you want to ask a question, you can just put one in the chat, or you can unmute your microphone. Anyway, so we're going to hear about Alison's work on approximating the inverse Hessian in 4D VAR data simulation. The Zoom window is all yours, Alison.
Thanks very much, Alex, and for the free plug for IFIS that you delivered there, and also, of course, for the invitation to speak in this seminar series. So the work I'm going to talk about today started life as a PhD project with Kirsty Brown and Igor Gajadze as co-supervisor. But since then, I've had very useful visits to Reading and good discussions with Amos Lawless and Nancy Nichols, which I wanted to acknowledge, and hopefully I'll be allowed to visit them again at some point not too far distant. So to start with, here's a slide on four-dimensional variational assimilation, or 4D VAR. So this aims to find the solution of some numerical forecast model that best fits a sequence of observations distributed in time and space over some interval. I'm not going to give you any of the details of this. Many of you will be familiar, and I know we've had already some seminars in this series talking about 4D VAR or applications to 4D VAR. So I'm just going to summarize that what we're doing is minimizing some cost function in terms of the analysis here, and it's got two parts. There's a term which relates the analysis to some background or short-term forecast in terms of the background error covariance matrix. And then over here, we have a sum over all the time steps of the relationship between the observations, which are these y's, and then this is an observation operator h here, and these are related in terms of the observation error covariance matrix. And all of this has to be minimized with respect to a constraint. And this is where the model dynamics, the underlying physics of the problem, are hiding in this model operator in here. So this is the basis of, for example, numerical weather forecasting, which is the application that I've really got in mind here. Specifically, I'm going to use incremental 4D VAR. So that means I'm going to linearize the observation operator in the model dynamics which turns the whole thing into an unconstrained optimization problem, which I can then solve iteratively. And brushing all the details under the carpet, I'm going to get straight to the Hessian, which is the main topic of my talk, which we're going to write like this. So B here is the background error covariance matrix. And then we have H hat, which has all the model information at the various time steps, and R hat, which contains copies of the observation error covariant matrices and is block diagonal. Okay, so this is the Hessian of the 4D VAR problem that I'm interested in. So why am I motivated to try and approximate the inverse Hessian? Well, the inverse Hessian represents an approximation of the posterior covariance matrix, which can be used for finding confidence intervals and carrying out some error analysis. Or, for example, the inverse square root of the Hessian can be used in ensemble forecasting. And the application that really led to me getting involved in this was that the inverse Hessian, or the inverse square root of the Hessian, can be used for preconditioning in a Gauss-Newton method. And that's my background, really. So this is the applications I'm going to show you are from the preconditioning area. So that's why we want to do it. What are the difficulties involved in approximating the inverse Hessian? Well, first of all of the vectors involved in this problem are enormous, as you can imagine in numerical weather forecasting. There's lots of sensors and lots of data. So the state and observation vectors can be very large. So typically, one probably can't store the Hessian as a matrix. All we have is the action of applying H to a vector. So we don't actually construct the matrix itself. And having said that, well, even evaluating H times V is expensive in terms of both computing time and memory. It involves forward and backward model solves with a sequence of tangent linear and adjoint problems every time you want to do H times V. So it's quite expensive. And no obvious equivalent option exists for evaluating H inverse times V, which is what we're interested in. You can't just easily invert each of the components in the HV procedure or anything like that. So we're going to have to do something a little different to approximate the inverse. So one useful step before we begin in earnest is to apply what I call first level preconditioning, or a control variable transform, as it's sometimes called. So this is my Hessian matrix. And basically, I'm going to precondition this on the back of the background covariance matrix. So we apply this preconditioning here to write the new Hessian, which is just a straight H rather than this double H here, in this form. So we've got the identity plus a lot of stuff. So the advantages of doing this, well, the eigenvalues of this new Hessian are bounded below by 1. And there are some papers written by people in the Reading group which go into more detail on the eigenstructure of this matrix based on the balance between the different terms and so on. But why I'm interested in this structure is because I'm going to construct limited memory approximations to the action of H inverse here. Okay, and that's going to be good because this matrix here has a large component, which is the identity. So from now on, whenever I say Hessian, I'm going to mean this H here, where this first level preconditioning is already applied. Okay, and as I've just said, we're going to look at constructing a limited memory approximation, and we can only use matrix vector multiplication. So just as an illustration, here's a picture of inverse Hessian from a test problem. It's based on Burger's equation. I'll give you more details of the problem later. So here, the matrix has been scaled to have unit diagonal, but I haven't plotted that unit diagonal here, otherwise you wouldn't see anything. So you imagine this one's down the diagonal, and this is the off diagonal action. And if we apply the first level preconditioning, then the new Hessian looks like this. So you can see the first level preconditioning has really brought the action in closer to the diagonal, and there's even less going on further away, which is exactly what we want with limited memory approximations. Okay, so what does my limited memory approximation look like? Well, I'm going to find a number of eigenvalues and orthonormal eigenvectors using the Lanczos method. That's fine, because for that all I need is h times v, which is what I've got. And then I'm going to construct an approximation that looks like this. So I'm sure you guys are all already familiar with this, but just in case there are people who haven't seen this before, the idea is, of course, I could take all of the eigenvalues here by choosing any to be large, and this would completely reproduce H. But for my matrix, I'm going to have a lot of eigenvalues that are close to 1, and only a few eigenvalues that sort of contribute more than that. So if the eigenvalues are close to 1, then of course this term is not contributing very much, and we can neglect them. So we want to keep any to be small, so we pick out a small number of important eigenvalues, and we hope this will be a good approximation. And what's going to be really important for what we do is that once we've got it in this form, then it's really easy to calculate H inverse and H square root inverse, because all I need to do is take powers of the eigenvalues. So we can flip back and forward between the inverse and the original Hessian very easily. So limited memory approximation has been used before for these sorts of problems in 4D-var as a preconditioner in a Gauss-Newton method, for example. So what's new about what we are proposing here? Well, we're going to add an extra ingredient, which is we're going to make the limited memory approximation a multi-level approximation. So here are some details on the sort of terminology and notation for setting this up. So I'm going to illustrate with a 1D problem. So I've got a sequence of grid levels. So level 0 is going to be the grid level at the top. That's the finest grid. And then we'll refine in the usual way down some multi-level structure. All we have to work with is the Hessian at level 0, the fine grid Hessian. Okay, and so I call that H0, and I'm going to assume all I can do is multiply H0 times a vector, right? Because we are not constructing this matrix. And the idea is we're going to make a multi-level approximation to the inverse of this guy at the finest level, which is what we want, based on limited memory approximations on this sequence of nested grids. So to do that, we're going to need grid transfer operators, which I'll talk about in a moment, and just a couple of pieces of notation. When I write IK, I mean the identity on the given grid level here. And then this notation with the square brackets means whatever matrix I'm transferring inside is being transferred to grid level K. Okay, so that's just the notation. So what about these grid transfer operators then? Well, let's start by thinking about transferring a vector and assume we've got two grids. One of them is a fine grid and one of them is a coarse grid. I'm also going to assume that I have some restriction matrix and some prolongation matrix. So these can be the typical things you would use with multigrid, so just linear interpolation, or you can use cubic splines or whatever, but we have these sort of normal restriction and prolongation matrices, if you like. And for the moment, we're going to assume that we've got perfect interpolation in the sense that this equation here holds. So if I take a coarse grid vector, I prolong it, then restrict it, then there's no error. Okay, so that's just to illustrate this next point. Let me now take my fine grid vector and split it up into two parts here. Okay, and then I'm going to apply the restriction vector to this and put it on the coarse grid. So notice if I apply that to the first, this red part here, given my assumption that R and P satisfy the identity, then this doesn't contribute anything to the transferred vector, and everything is coming from the transfer of this second part. So in other words, the modes in this part 1 of my vector here are not supported on the coarse grid, and I don't need to transfer them from grid to grid. There's no point in doing that. Oh, yeah, I see a question here on the chat. Apologies. Yes, of course, R is a restriction matrix here. I never noticed in all the times I've thought about that I shouldn't have called it R, but it's nothing to do with the previous covariance matrix. This is just a multi-grid type restriction. So thanks for that. Right, so we've got this part of our vectors, which are, there's no point in transferring them from grid to grid. So let's take that idea and add it to our grid transfers for matrices. So let's suppose now we've got the coarse grid matrix that we want to apply to a fine grid vector. So here's my notation. I'm going to somehow transfer that up to the fine grid and apply it to VF. But we know there's no need to apply it to the red part. So we just do the usual to the black part. We restrict, we multiply, and then we prolong back up. Okay, so doing the algebra means that this is a sensible representation of this transfer operator. So these are the matrix transfer operators that we're going to use from coarse to fine grid and from fine to coarse grid. So one way of thinking about it is we know that our matrix is mostly sort of consists of the identity here, or a lot of it does. If we transfer that back and forth from grid to grid, we're just going to get errors. So basically we take out the identity part, transfer that in the usual way, and then we say, well, we know the identity should transfer to give us the identity on the fine grid. So we add that in. Okay, so whenever you see this square bracket notation, that's what it's going to be. So now we've got all the ingredients for our multi-level algorithm. You might be wondering, what's the point of this? What makes you think this is going to be a good idea? So let me try and convince you that it looks like a good idea. So in this picture, we've got diagonal of the inverse Hessian on various grid levels. So this is for the same model problem we saw earlier on. It happens to have 7 sensors, which is why we've got these 7 peaks. The different grids are given by the different lines here. The solid black one is the one coming from the finest grid. So this is what the inverse Hessian diagonal should look like. And then the other lines are indicating what the same thing looks like on the coarser grids. So you can see if we go one level down to the red dashes, this is pretty good, still following the same sort of path. If we go 2 levels down, well, we still get something going on with this green at each of these spikes identified. And even if we go 3 levels down, then okay, this bit in the middle is rotten, but there's the bits at the edges are still capturing something of the problem. So it looks like the lower levels have some relation at least to the highest level inverse Hessian. And in fact, here are the eigenvalues of the Hessian at each level. So this is at the fine grid Hessian in black here. So of course, transferring that to the fine grid, nothing happens. These are the same. If we transfer this Hessian to 1 level down, then this is the eigenvalues of the result. If we take it 2 levels down, they look like this. If we take it 3 levels down, they look like this. So essentially, it looks like we're still capturing quite a lot of the eigenvalue spectrum by going down to lower levels. So this leads to the motivating idea, really, which is very straightforward. If you're used to preconditioning, that is, we expect that the eigenvalues of the fine grid Hessian preconditioned by the eigenvalues of the coarse grid Hessian should be clustered around 1, because the matrices have similar structure. And of course, the added ingredient is that these need to be transferred to the right level. Okay, so we take the coarse grid Hessian and essentially use it to precondition at the level above. So that's the motivating idea. What we're going to do in practice is we're going to construct an approximation to this HC minus a half in here on our coarse grid, and then we're going to transfer it up a level to use as our preconditioner. Okay, so here's how we do that. And now there's an additional ingredient and an additional level of preconditioning, which I'm going to introduce. Remember that I want to use limited memory approximation here. That's going to be good if the eigenvalues are all clustered around 1. So the first thing we do with our coarse grid Hessian here is we precondition it to make the eigenvalues closer to 1, so we get a better limited memory approximation. That's the idea. So I haven't told you what M is yet. We're going to do that in a couple of slides. but just assume for now we can precondition to make the eigenvalues closer to 1. We can then build a limited memory approximation to this preconditioned HC, which I've called HC hat here, using eigenvalues calculated with the Lanczos method. Okay, so that's okay. We've got our matrix times vector. And here's the key point. Notice from this relationship here with HC twiddles, we can write the inverse of the coarse grid Hessian like this, and then we can approximate that using our limited memory approximation. Or what we want here is an approximation to the inverse square root of HC, which is this guy here. So we can replace HC inverse by our preconditioned coarse grid limited memory approximation. And remember, this is easy to get from the eigenvalues just by taking powers of the eigenvalues. Okay. So this is the main idea of how we precondition at one level using the level below. Okay, so we construct this matrix here, and then we take it to the fine grid, the level above, and we apply it as a preconditioner. And we're doing it to keep everything symmetric. Everything's symmetric, positive, definite here. We're going to use PCG, so we want to apply everything symmetrically. Okay. So that was the sort of 2-grid version. For the full multi-level algorithm, what we're going to do is we're going to start on the bottom level. So we start at the coarsest level, and we transfer the Hessian down to that level. We can precondition that using our M's, which will come in a moment, build our limited memory approximation, and then project that up to the next level to be used as a preconditioner. Okay, and then we go to the next level, we do the same thing, and we work our way from the coarsest level up to the finest grid. So it's a full multi-level approximation. So the last ingredient we need here is the preconditioners. What are these M's? In our first step, we're at the coarsest grid level, so there's nothing underneath. So we simply use set MK to be the identity at the coarsest level. Okay, but then at the other levels, MK is constructed on the level below and applied at level K. And here's the key point. These preconditioners are constructed recursively. So what it means is as we move up through the levels, we're collecting information about the eigenvalues on every grid. Okay, so once we get back up to the finest grid level and we've got our full preconditioner, which are called H inverse approx, that is going to contain eigenvalue information from all of the grid levels, and that's what's going to mean it's a viable approximation. Okay. So I hope you've kind of got the gist of that. I know the details of it is quite complicated when you see it all at once like this. And of course, in practice, we don't really do any of this at all, because in practice, all we're doing is we are using the Lanczos at every level to calculate eigenvalues and eigenvectors, and then we just combine them in matrix vector multiplications through the limited memory approximation and the preconditioning and so on. Okay, so the algorithm itself is essentially looks like this. We need to decide how many eigenvalues to keep at each level of the approximation. But once we've got that, we put in that information together with the top level matrix, and then we work our way through all the grids, calculating all the eigenvalues and eigenvectors that we need. That's the result of our algorithm. And then to do H inverse times V, we just put them all together in the right order, okay, including these grid transfers, which I defined. So just to comment on the storage, the memory requirements here. So after we've done this process, we're going to have a load of eigenvalues and eigenvectors on the finest grid, which are blue here, and then black at the next level down to the coarsest grid. So of course, in terms of storage, the length of these eigenvectors is important. At the finest grid level, they're twice as long as the next level, and so on all the way down. So I can store 2 black ones for the price of a blue one, and so on all the way down to the red ones at the bottom. Okay, because that's going to be an important ingredient as we want to try and reduce storage. Right, so now we've got an approximation. which we can build using this algorithm. And the question is it any good? So of course, I'm going to tell you it is, otherwise I wouldn't have spent all this time telling you all about it. So we need a tool for assessing approximation accuracy. And in what we're doing here, remember, all we've got are these eigenvalues and eigenvectors, but luckily here's a measure which we can use, which is based solely on the eigenvalues. Okay, so we're going to use a Riemannian distance as a measure between two matrices, which is based, can be calculated just using the eigenvalues of our matrix. So that's straightforward to do. And we're going to put this into a distance function. So comparing the eigenvalues of our two matrices on the finest grid level, we're basically going to calculate this distance and we're going to normalize it so that this measure capital D, if we've got a really good approximation, should be close to 0. And if we've got a poor approximation, it's going to be close to 1. So this is a number that I'm going to show you for the approximations that I'm about to calculate. Okay. And we're going to vary the number of eigenvalues chosen on each grid level to see what the difference is in the approximation. So here's the information I promised you about the test problem. So in this case, the model is a one-dimensional Burger's equation, which is quite often used to test these data assimilation problems. That's discretized on a fine grid to represent the full Hessian H0, and at each grid level we then throw away half of the grid points as we move down. We've got a one-dimensional uniform grid with 7 sensors at these particular points, so that corresponded to the 7 spikes you saw earlier on in the diagonal of the inverse Hessian. And I'm going to take 4 grids, so it's just a small problem, start with 401, and then the courses grid has 51 grid points. So now I'm going to show you some pictures of eigenvalues. The top level Hessian on 401 grid has 401 eigenvalues, of which the first 70 are plotted here as the blue circles, okay? And the rest of the eigenvalues are 1, so haven't bothered plotting them. All right. If we have a lot of memory available and we can afford to keep, I've taken 64 of the eigenvalues in my top level limited memory approximation. Okay, so this is just vanilla limited memory, I haven't done any multi-level. Then I get the approximate eigenvalues, which are the red stars. So the first 64 of these are exactly equal to the eigenvalues of in the exact case. The rest of them are approximated by 1, but of course it doesn't make much difference because they're very close up here. Okay, so this is great and D is very small. So that's fine, but that means we have to store 64 of these enormous vectors. So let's now suppose that we can't do that and we have only enough memory for storing 8 of these eigenvectors. Okay, so that means we take the first 8 eigenvalues and then we assume that the rest of the eigenvalues are 1. So this is not looking so good, and obviously D has correspondingly got much bigger. So this is the sort of limited memory approximation that's been used before in data assimilation, okay, where you just throw away the rest of this information. So the question now is, can we do better than this using the same amount of memory? So if I take the same amount of memory here, but rather than having it all in terms of eigenvectors at the finest grid level, can I get a better approximation? And again, the answer, of course, is yes, I can. So in this particular example, because it's small, I can try all possible combinations of eigenvectors, and it turns out that the one that gives the smallest value of D here happens to be taking no eigenvectors at level 0 or at level 1, 29 at level 3, and 6 on the courses grid. Okay. And when we look at the eigenvalues of these, the approximation, you can see it's somehow representing a bit more information here compared to what we saw before. Okay. So this is good, but of course I found this best combination by trial and error, which is not going to be any use in practice. So we had to think of a way of trying to work out how we should choose how many eigenvalues to take. So let me try and persuade you we have a good rule of thumb for doing this by looking at the following. So now think about a fixed memory ratio R, which is along the x-axis here. So we've just looked at R is equivalent to the number of eigenvectors at the finest grid level. So we've looked at R equals 8 in that last picture here. Okay. Down the y-axis, we have the distance, and this line at the top here is the distance if you take all of your memory at the finest grid level. So using the vanilla version of limited memory approximation, this is the line we would get. And if you have enough memory, then this is clearly going to be better eventually than what we're doing here. That's fine. So the 64 that we had at the beginning is way off here somewhere, and that will be better. But we're focused on saying, if you want to keep your memory low, can you do better? So the dashed line and the solid line here are the true minimum and the average minimum, when again, I've tried all possible combinations here. So clearly we can make a big improvement in reducing D here compared to just using everything at the top level. The problem is, how do we characterize this minimum in practice? And so this is where our rule of thumb came in. And we developed what we call this doubling strategy. And that basically means we take twice as many eigenvectors and eigenvalues as we go down the grid level. So if we take 2 on the top level, we take 4 on the next, 8, and then 16. And it turned out that this doubling strategy, although it's not the exact minimum, it is very close in some places, not so good in others, it's basically not too far away from the minimum strategy in each case. So that is basically what we've adopted as a rule of thumb in practice when we've been applying this. So that sort of gave a comparison directly of the matrices. In practice, as I said, we're going to use them to precondition the Hessian. So here's the same examples now with the preconditioned spectrum of the Hessian. So this is the original. If we take all our memory, or 64 fine grid eigenvectors, that's great, but it was a lot of memory, but obviously it's a really good preconditioner. If we take these are the two that I showed you the eigenvalues of, 8 at the top level, and then our sort of best case here. And then this is just a sample of our doubling strategy in between. Okay, so it looks like we're going to achieve something with our preconditioner. So here's a specific example where we take a PCG iteration just for 1 Newton step. So typically we're solving a Hessian linear system within a Gauss-Newton method. We're going to use PCG because that only needs H times V, because that's all we've got. And so here are the results. In terms of storage, everything's normalized so that capital L is the length of an eigenvector on the finest grid. So that's 401 in this problem. And the solve cost is also normalized with respect to the Hessian vector product on the finest grid. So what do the results look like? Well, if we don't take any preconditioner for this particular system, it took 57 iterations, but of course we don't need any storage, and it's going to be 57 Hessian vector products to solve this. If we're absolutely crazy, but this is really just as a sanity check, and we take almost all the eigenvalues, we've basically built the inverse, and we're pleased to see that that gives us convergence in 1 iteration. Otherwise, we know we've done something wrong here. But of course, we've had to store all of these eigenvectors, and the solve cost is going to be very expensive for the preconditioner solve. So here are 3 methods where we've used our doubling strategy. This one uses information from all of the levels. So the iteration count has gone up slightly, as you might expect, because the approximation won't be so good, but the storage and solve costs are much, much smaller. And as we throw away information on the finer grids, then we see the same thing. The iterations will go up, but actually our costs are much better. So it looks like this is working fairly well. If we then take a full Newton solve from start to finish, then this is what the results look like. So a couple of things to notice here. First of all, the axis along the bottom is the number of Hessian vector products. So it really is a solve cost here. It's not the number of iterations. And that's plotted against the log of the gradient norm. The second thing is that because we're using a Gauss-Newton method, we let things settle down a bit before we apply the preconditioner. So we haven't switched the preconditioner on until we get to this point here. So you can see that in terms of the solve cost, then all of the methods that we've looked at on the previous slide are working well across the whole simulation. So that was a promising start. A second test problem we used is for the shallow water equations here. So we're solving now for velocity u and geopotential phi. It's another problem typically used in data assimilation for testing. And I realized before Ilse asked this time that h has got nothing to do with the Hessian. It is the height of the ground at the bottom of the water. So it's another contradiction in notation, and that little h is the shallow water itself. So this time we've got uniformly spaced sensors. We've still got a 4-grid multi-level structure. And here are results for 1 Newton step with a background covariance matrix first constructed using a Laplacian correlation function. And this time the problems are a bit bigger. So we start with 400, which is our previous problem level, and we're going up here. So of course, with no preconditioner, then things will grow. The rest of these are a selection of our preconditioner, but they all use the same memory this time. Okay, so all of these combinations are using the same memory. And what you can see is that across the columns here, as we're growing the size of the grid, it looks like we've got some sort of grid independence. It's not perfect, but it's certainly not growing in the way that the unpreconditioned iteration counts did. Here's the same experiment again, but this time with a SOAR correlation function. So it's a little bit more challenging for PCG, but we see similar results across these columns. So far so good. This has all been a very nice, rosy story. But if you've been paying close attention, you'll realize I was very carefully talking about solve costs when I looked at these results that I showed you, and I didn't mention the cost of actually constructing the preconditioner in the first place, because of course when we're constructing an approximation of the inverse, but essentially we can do that separately and then just apply that as the preconditioner. And it turns out that of course that adds to the expense of the problem. However, we do have practical ways of getting around that when we're implementing things. And the key idea in that respect is to use a Hessian decomposition. So the idea here is that we partition the domain into capital S subregions. So this will typically be one per sensor. And we can compute local Hessians and then assemble them together to make a global Hessian. So I think of this a little bit in a sort of finite element way, where you calculate your finite element matrices and then you assemble them to get the global matrix. And I think it makes sense because it's reasonable to think that when you're taking information from a sensor, it's going to have more influence in the structure of the Hessian close to where it is rather than to what's happening somewhere further away. Okay. So why is this useful? Well, there's many computational advantages of doing this. First of all, these things are going to require fewer eigenvalues for limited memory approximation because they're going to be more localized and they'll have less information that's different from the identity, if you like. As all we're doing is building approximations, we can actually calculate these at coarser grid levels, if we like. We wouldn't need to have the Hessians calculated at the fine grid level. In theory, we could use local rather than global models. So I said back at the beginning, when you're evaluating H times V, you have to do these big model solves, forward and back model solves. Well, for a local Hessian, you could do that on a local scale. And then, of course, in principle, these things could also be computed in parallel. Okay, so I should say these last 2 points here are not implemented in the results that I'm going to show you, but they would make the results better because they represent even more savings that can be made. Okay. So what's the practical version of the algorithm look like? Well, here's version 1, where what we do is we compute limited memory approximations to these local sensor-based Hessians on a given level. mostly the fine grid level, sometimes a level below, using a number of eigenpairs. So here's our limited memory guy again to these local things. We assemble these up to form some assembled Hessian, and then we apply our multi-level algorithm to HA in exactly the way that we did it before. As I mentioned, the advantage here is that local Hessians are cheaper to compute, but there are disadvantages because now we've got yet another set of parameters in here, right? We can again fiddle about with these, there's endless, as my PhD student will testify, there's endless fiddling with parameters to be done in this whole setup. So we've now introduced another load here. It also requires more memory because you also need to store these local Hessians. Okay, so that may be, again, a disadvantage. However, if you use this setup, then here are sample costs where this time they really are including building the preconditioner. Okay, so solve plus building preconditioner, again in terms of the number of Hessian vector products rather than iteration counts here. So there are two sets of results. Well, the black line represents what happens if we do nothing. And then for the other results, the solid lines are where we've calculated the local Hessians by taking 8 eigenvalues. I've just fixed that NK from the last slide to be 8 here. So the solid lines are where the local Hessians are calculated at the finest grid level. And the dashed lines are where they're calculated at level 1. So that's going to be cheaper because the matrices are going to be smaller. Okay, and so you can see the comparison here that in general, we've saved some time and memory by calculating the local Hessians at a lower level, but it has not degraded the results. Okay, so with this setup, we've now got something which is competitive, including building the preconditioner. Here's a second practical approach, which may be a little bit pathological for those of you, particularly if it's very early in the morning where you are. I'll apologize for that. Because what we can do is we can apply our multi-level algorithm twice, and this is going to reduce our memory requirements. Okay, but here's where the sort of twisting your brain comes in, because what we can do is we can approximate each local Hessian by applying our multi-level algorithm to the local inverse Hessians. So if you remember, what we're doing is what we've been doing so far has been approximating the inverse Hessian by putting in the Hessian and getting out all the eigenvalues. Of course, we could do it the other way around. We could put in the inverse Hessian and then approximate the original Hessian. So we can do this at the local level and then use our multi-level algorithm to represent this in a limited memory way. So that's going to reduce the storage for local Hessians. We can then assemble these in the same way to get a reduced memory one, and then we can do the same procedure with our global algorithm based on our number of eigenvalues at each level. Okay, so this is a trickier one to get your head around. It does have the advantage that it needs less memory than version 1, but again, we've introduced more limited memory approximations, so we've actually got yet more parameters in here that we need to think about. However, it might have use in particular settings, because one thing to remember in this forecasting business is that there can be different problems. So if you want to actually forecast the weather, then you want to be able to do that now as fast as possible, but you might have a really big computer with lots of memory if you're in the Met Office or whatever. So having some additional memory wouldn't be a problem. However, if you're doing some of the other applications, which is the a posteriori error analysis, for example, then you might not be worried so much about computational time because you're not doing that to a deadline, but you might have a smaller machine that needs to use less memory. So it's a bit of horses for courses. Some of these methods would work better in different circumstances. Okay. But let me just show you the results for using this version. So this is, again, the cost including building the preconditioner. It's the same as before, that the solid lines are the local Hessians with 8 eigenvalues at level 0 or at level 1. And for the first multi-level approximation, we've taken 8 and then 4 eigenvalues here. So for this particular example, it turns out that in some cases we've kind of gone too far with our approximation now. So taking it one level around, for example, with this green line here, that's going to be worse than doing everything at a fine grid level. But in some cases, then this still gives us an improvement overall. Okay, so just to summarize then, what I have shown you today is an algorithm which is based solely on repeated use of Lanczos at each time level for building these limited memory approximations. Okay, so they're based on the idea of limited memory, which has been used before in these enormous problems, but the difference is this multi-level concept. Unfortunately, it's difficult to identify the right number of eigenvalues to use at each level, but we have got a good rule of thumb, which seems to work well. Of course, analysis would be even better. And if anyone in this hopefully global audience has wonderful suggestions of how to do that, that would be very, very welcome indeed. The full algorithm might not always be practical, but we have got practical versions based on these Hessian decompositions, which will be interesting to try on other problems. We have looked at different configurations, problems with moving sensors, for example, because quite often there may be an aircraft or something might be taking readings. So we have tested for those at different initial conditions and so on, and there are two types of problems. So that's all looking good. And as everyone always says at the end of their talk, there's definitely potential for extending to higher dimensions. But here, you can see the only thing that I can envisage that might be an issue here is the grid transfers, i.e. what's our choice of P and R going to be, but these issues are well understood by multi-grid people for multi-dimensional problems. So hopefully we could slot these in here, then there's no reason that this wouldn't work just as well for higher dimensional problems. And maybe just one final remark, the method as we've described it is not unique to the inverse Hessian as coming from these 4D var applications. It could be applied to any matrix. It's not going to be great if your matrix is not amenable to this limited memory approximation, but there may be other situations, other optimization problems, for example, where you have a matrix which has this structure of the identity plus a few distinct eigenvalues that are nothing to do with my particular application, but the method would still work in exactly the same way for those problems. So there's definitely potential for this to be used out with the narrow confines of 4D var that I've talked about today. But I will stop there and say thank you very much for listening.
Okay, thank you very much, Alison, for a very thought-provoking talk. I will clap for everyone. Do we have questions? You can just unmute.
Yeah, may I ask one? So when you talked about the inverse Hessian, I probably didn't pay attention, but I thought the Hessian wasn't explicitly available, or was that some other matrix? I missed things.
No, all that we have available is the Hessian times the vector. So we can use that in Lanczos to get the eigenvalues. Let me just go back perhaps to the, so we've got, here we are. So we can multiply H times V in Lanczos to get some eigenvalues. And then to get the inverse, then all we need to do is take 1 over the eigenvalues in here. Right, so the only thing we have is H times V, but the way we can turn that into an approximation to H inverse or H minus a half is through the limited memory approximation.
Oh, I see. Okay, thanks.
Yeah.
And so when you do these local Hessian approximations, is that equivalent to approximating it just by a block diagonal matrix then? When you break it up into S, into the regions S?
No, it's not as simple as that in terms of the this sort of assembly process here. It's more akin to finite elements where you have got local element matrices, but then the entries of these go all over the global matrix, if you know what I mean. So there is some sort of it's not just as straightforward as block diagonal.
Okay. Yeah. So it wasn't also clear to me why you had to store all the local Hessians rather than just have available their actions on vectors. Would it be okay to have just their actions on vectors?
Yeah, I guess so. I mean, that's in a way that's the difference between this version 1 and the version 2. So in version 1, we're storing the Hessians, but then in version 2, we're using the algorithm to construct them and apply them without storing them.
Okay.
That makes sense. So yeah, that gets rid of that. The first one is just sort of proof of concept on this assembly of Hessians. If you've got enough space to store these additional things, so they're not going to be huge, but they're still going to be the additional storage, then you would need to keep those. Whereas with the second version, you're doing the application through our multi-level process, so you don't need to store them there.
Okay, very good. Do we have any further questions? If not, we will thank Alison again.
Thank you very much.
And we're going to meet again in 2 weeks' time. Jack Dongera actually is giving the next one, the recent Turning Prize winner. So I look forward to seeing everyone there in 2 weeks' time. If not, we can hang around on the Zoom call for a little bit. Don't feel like you have to go. I guess we'll keep this going until 11.